Hey, it's Mr. Allred, and we just talked about how to rewrite logarithms using the definition of logs. So here I'm going to show you how that can be useful as far as simplifying logarithmic expressions. So the first thing we have here is a logarithmic expression, and it says log base 5 of 125. And the thing about this is there's no variable in there. All we see are numbers. So there's the log function, this base 5, and the input is 125. So if I want to kind of figure out what that is, and I'm kind of early on in my stages, I might give it a name. So I'm going to say this thing is equal to, let's say, z. I don't want to use x and y since they were used in our definitions. And if that's the case, now that I have that, I have all three pieces that would allow me to rewrite it as an exponential equation. So it would be base 5 raised to the exponent of z equals 125. And the reason this one's going to be doable is because you may notice a relationship between 5 and 125. So we can rewrite 125 as 5 cubed. And in that case, we have an equation where we have the same base on each side. So these exponents must be the same. So z must be 3. So this statement up here, log base 5 of 125, must be just a fancy way to write the number 3. Okay? So we converted to an exponential equation and used a little bit of logic in our rules of exponents here. The next one is log base 3 of 1/9. So I'm going to do the same thing I did before. I'm going to set it equal to make an equation, and I'll call it equal to z. Okay, if I do that, then I can rewrite an exponential form as 3 to the z equals 1/9. Now, there's a few things that we could do here, a couple of steps. Once again, we know there's a relationship between 3 and 9. So let's see if we can get there. We can keep the 3z, and we can rewrite 9 as 3 squared. So we'll have 3z equals 1 over 3 squared. So then I also know that I have my negative exponent rules. I can bring that 3 squared from the bottom to the top, and it'll be 3 to the negative 2. So once again, I have like bases, both base 3, and both of them have an exponent position. So I can look and compare those exponents positions, and I'd say z equals negative 2. So again, this log base 3 of 1/9 is just a fancy way of writing negative 2. Let's do a couple more. So here, log of 10,000. Okay. I don't see a base here, but we can understand, remember that if there's no base written with the log, it must be base 10. So again, I'm going to give it a name. I'm trying to avoid picking up a calculator yet. But if I call it z, then I can rewrite it exponentially as 10 to the z equals 10,000. Okay, and 10,000 is the same as 10 to the 4th. So you still have to work a little bit for these. So both sides are base 10. So the exponents must be the same. So when we do get to a calculator, and you can enter this very easily, or even if you know how to do it now, log of 10,000 should give you 4. Okay. The last example before we move on to some simplifying rules, log base 4 of 64. I'm going to do the same thing I've been doing. Set it equal to some variable. Call it z. So 4 to the z equals 64. There's a couple different ways you could do this, but the easiest thing is if you do know that there's a relationship between 4 and 64. I know you're looking at 64 and saying that's 8 squared, but it's also 4 cubed. So that might not be something that you know right off the bat. But just like with the rest of them, we can say that z equals 3 because of that. So log base 4 of 64 is a fancy way of writing 3. So we're not going to get nice answers out of every one of them, but we will be able to do them. So let's see here. I have some simplification rules here, and there's the first column, which is for any base, and you could also see that as the common log if you replace the base a with 10. And then my second column is the natural log rules using base e. These are all really the same rules if you move left to right. Each row is the same rule, just wanted to make sure you had both forms. But let's talk about them real quick. Log base a of 1 equals 0. Basically, a to the 0 equals 1. Anything to the 0 equals 1, so that rule makes sense. The equivalent in the natural log form is natural log of 1 equals 0. So more or less, that first rule comes out of the fact that a to the 0 equals 1. That's where that rule comes from. The second row, log base a of a equals 1. So if I rewrote that, it would be a to the first equals a. That makes perfect sense. The equivalent would be natural log of e equals 1 because that's base e. So over here this is e to the 0 equals 1. I guess I'll go ahead and write these out. E to the 1 equals e. The next one, log base a of a to the x equals x. So if I convert that over to exponential form, it'd be a to the x from the base and the exponent equals a to the x. And natural log of e to the x equals x. So once again, that's understood to be base e, so e to the x equals e to the x. All these things are lining up very nicely. The last row here, a raised to the power of log base a of x equals x. So that was an exponential form. So I'm going to change it to a log form. It would be log base a. And what's it equal? What goes inside the argument? The x from this side equals the exponent, log base a of x. So it makes sense. The other one, e to the natural log of x equals x. So once again, that's in exponential form. So I can write it in log form. ln for base e of x equals natural log of x. Okay, let me do a quick little thing here. Try to make sense out of it. Let's see here. Let me undo that. Let me highlight the exponents for sure. So here's the exponent, here's the exponent. I'm just going to highlight the exponents in all these cases so that you can kind of make sense of them. That was log base a. Oh, that's that's not the exponent. I'm fumbling here, sorry. There's the exponent, and over here we can put it on either side. Same thing here. Just highlighting the parts that would be the exponent, so that you could relate that as we need them. Okay, so let's just kind of use those rules a little bit. So a couple of simplification rules. Make sure you can see where these things come from. The first example I have here is the natural log of e to the 7. So if I come over here, I see that that kind of fits the second column, the natural logs. It fits the third rule, natural log of e to the x equals x. So by that rule, this thing is just a fancy way of writing 7. I don't have to go through the conversion. Okay. The second one, log of 10. Well, let's come over here. That's understood to be a base 10, if you want to write it in there. So it's base 10 of 10, so that's log base a of a. That is this rule right here. So that's going to be 1. So this rule here, it might help to kind of link them up. The fourth one, log base 5 of 1. Let's use a different color here. That kind of fits the log base a of 1 equals 0. So anything to the 0 power is 1, so that equals 0. And the bottom one here, natural log of e, well, that rule is kind of explicitly on the other side. That would simplify down to be just 1. There we go. So take a look at those and make sure you can identify the parts and why I'm able to simplify them. Okay, just following those rules making sure everything's in the right form. All right, so the next set I have here is a little bit more complicated. They don't start off in perfect form. So I've got log of 1,000. So I'm going to rewrite that as log. It's understood to be base 10, so I'm going to write it as log of 10 to the third. And then when I do that, I can look over here and see that it fits the log base a of a to the x. So this thing is going to be 3 because that's the exponent that came out of it. The next one, log base 5 of 1 over 25. So we're going to change 5 to 5 squared, and we're going to bring it up as 5 to the negative 2 exponent. So that is technically the exact same rule we just used. Okay. And the last one down here, 6 raised to the log base 6 of 4 to the x. That is the last rule where the base of the exponent and the base of the logarithm match. So in that case, a equals 6. And if you match everything up, this thing here will simplify down to 4x. So if we can find common bases between the logarithm and the part that we're trying to simplify, usually there's a rule that will let us do that. Okay, it's going to take some practice and some getting used to, but hopefully with enough practice we'll get there.